a function. We can talk about where those are little nuanced differences between the derivative at a point versus the derivative as a function. All right, so we're basically expanding what we worked on for the past 2 days and trying to see if we can even further formalize our idea of the derivative. So this is what, long story short, what we covered last time. So last time we talked all about if I have a function and I have some a value, then the derivative of my function f at a, where we use this notation f prime of a. For example, we might say f prime of 4, f prime of 7, f prime of whatever number. We had this limit definition of the derivative at a point. And this was given by f prime of a is equal to, our first version was the limit as x goes to a of f of x minus f of a all over x minus a. But with just some refocusing our idea of what we know about functions, we could say that this was equivalent to saying the limit as h goes to 0 of f of a plus h minus f of a all over h. So this is what we talked about before. So for example, if I just gave you some random function like something like f of x equals 3x, and I said look at the point a is equal to 3, then we could find the derivative at 3. For example, through all of this algebra work, we can figure out what f prime of 3 is. So we had a whole process for this. And usually, to recap what we did last time, I highly recommended that we use the second definition. And then we start off by finding f of a plus h, f of a, and then working on it from there. So this is fine and good if I want to give f prime of 3. But what if I suddenly gave you instructions where I said, all right, we have f prime of 3, now give me f prime of 7, f prime of negative 4, f prime of 19. And looking at this, the way that we've been doing it so far, that's a little bit troublesome because that means I would have to do this limit definition 3 times in a row, 4 times, I guess. I would have to do one for whenever a is 3, when I have 7, when I have negative 4, when I have negative 19. Obviously, we don't want to just keep on doing all this algebra work over and over again. So instead, what if I think about my derivative as a function? That is, what if I can figure out some f prime of x? Where instead of trying to figure out what these are individually each time, what if I can find a function representation? That is, if I can find an f prime of x, and then if I can figure out what this is, then I can just plug in 3, then I can plug in 7, then I can plug in negative 4, and plug in 19 individually. So let's see if we can try to streamline finding the derivative just a little bit. So this was f prime of a, the derivative at a. Let's go ahead and expand our definition of our derivative by just one letter, it looks like. If instead of the derivative at a, what if I just want the derivative of my function in general? And actually, this is going to turn out to be the form of the derivative that we're going to use more often compared to f prime of a. The derivative of f, which we denote with f prime of x, is this function. F prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. And this is under the assumption that the limit does exist. If I did all of this algebra work, we could find the limit. So now instead of the derivative at a number, I can find the derivative as a function. if I can find a derivative as a function, then I can just start plugging in different numbers if I want it like f prime of 7, f prime of 9, f prime of whatever number you want. So if I look at this limit definition of the derivative, this formula right here, someone tell me, how is this different from what I had on the previous slide? What were some just the one big difference? Here we have denoted as f prime of x. So the first thing we note is before I had f prime of a, and now I have f prime of x. Whenever I said f prime of a, let me go ahead and write that on the side. Whenever I wrote f prime of a, I would be doing something like f prime of 2, for example. In other words, I would know what a is, and then we would do all of our calculations with a is equal to 2. But in this case, f prime of x, I'm leaving that x alone. I'm not going to be plugging in for x. I'm not going to be plugging a number in, at least. Again, I'll say it. We're looking at the derivative as a function. Something that instead of finding the exact value, I can start plugging numbers into that expression. So before, if I wanted f prime of 2, I would just plug in a is equal to 2, do all of this algebra and all of that. However, for this case, I would do a very similar process where I would get f prime of x, and then I would get some expression. This might be something, I don't know what it might be. But whatever that expression might be, if I still wanted f prime of 2, I could just take this function and plug in 2 afterwards, after I've already done all the cleanup work. Right now, it's a little bit abstract because we haven't really done an example just yet, but you'll see what I mean in a moment. All right, so the other question I'll ask is, does anyone remember what does it mean to be differentiable at a? What did it mean to be differentiable at a? Or differentiable at a point? Well, it definitely involves a derivative. If we recall, differentiable at a point A just means it was possible for me to get the derivative at A. In other words, I know what f prime of A is. It's some value, whatever it may be. It's not undefined. Yeah. So if I want to be differentiable at A, that just means whatever this thing is, it's equal to some number. It's not just undefined. I could say, for example, f prime of 2. If I did all that work like last time and I got, I don't know, 4, then I would say my function is differentiable at 2 because I can find a derivative and it's some number. So that's what I meant last time whenever we said differentiable at A, or if I said differentiable at 7, that meant I know what f prime of 7 is. It's possible to get it. It might not always be a clean number, but it's defined. I'm not like dividing by 0 or taking the square root of a negative. So that was differentiable at a single point. I can say that a function is differentiable for a range of numbers, so like an interval, if I can find a derivative at every single point in that range or in that interval. So all this bottom definition is saying is, instead of saying differentiable at a single point, I can be differentiable among a big range of numbers. It's technically still the same definition. We're just saying instead of looking at a single, we're going to look at as many as we want. If I wanted it to be a little bit technical and use some fancy wording, then really I would be saying differential means that the derivative does exist at that point. Again, right now, just a bunch of letters, words that are going around. We're going to hold off on some questions and then do an example first to see what's going on here. I'll give you a couple of people some time to copy this down. All right, so let's go ahead, and I believe if I timed this correctly, should be example 1. There we go. Example 1. Let's say I got this function here, 2x squared minus 1. Find the derivative f prime of x using that limit definition of the derivative that we just worked with. And just so that we have it for reference, I'm going to go ahead and write that limit definition again on the top. F of x plus h minus f of x all over h. So that's just me copying what was on the previous slide, just so that we have it on the board. So if I'm looking at this originally, before we did f prime of a and we did f prime, now we're doing f prime of x. So it looks like we didn't really change much in our notation. It's that instead of plugging in a number, we just have a plain x. So the good news about this compared to last time is that actually we're going to be doing the exact same thing. We're just going to be, instead of plugging in a number, we'll leave it as an x. So last time, whenever we wanted the derivative at a point, the way that I presented it to y'all was I focused on this portion and figured out what f of before a plus h was. I'll do the same thing here and figure out what f of x plus h is. I'll figure out what f of x is, and I'll figure out what everything is individually. And actually, we might be able to save a little bit of time here. So let's go ahead and focus on this highlighted part. Let's focus on what f of x plus h is. So again, we're back to the idea that it's really going to be testing our algebra skills. Do we know what does it mean to plug a number in? All right, so if I want f of x plus h, but I have f of x. Remember, whenever I write something like this, it's telling me anywhere that there's an x in the original, I'm replacing it with an x plus h. I'm not just adding h at the end of this. Anywhere there's an x, I'm replacing it with an x plus h. So that would give me 2 times x plus h squared minus 1. So again, I didn't just say plus h at the end. This is me anywhere that there's an x. I swapped it out for an x plus h. So what I'm going to do is I'm going to try to clean this up as much as possible. And by that, I mean, let's get rid of the parentheses and the squaring. So just for notes, I want to remind y'all that whenever I do x plus h squared, that is the same thing as me saying x plus h times x plus h. So just a reminder for what x plus h squared means. It's not x squared plus h squared. It's x plus h times x plus h. All right, so it looks like the most complicated part of this expression is a x plus h times x plus h. But in the end, it's a binomial times a binomial, meaning I can do my little old FOIL phrase. So the 2, I'm going to keep it the same for now. if I want to multiply these two expressions, again, f first times first, we have x times x, giving me x squared. If you want to write the little f there, you can. O is for the outsides. So x times h, I just get xh. Next are the insides. What do I get whenever I multiply the insides plus what? Yeah, we get xh or hx. You might write down hx just because you see h first, but remember, multiplication, we can swap it around. X times h, same thing as h times x. Just has how you would think 3 times 4, that's the same thing as 4 times 3. The order doesn't matter whenever you multiply. And then L last times last, we get h times h, giving me h squared. And I still have this minus 1 at the very end. All right, how can I take this one step further to clean it all up? Where can I go from here to try to either combine like terms or get rid of any parentheses? Yeah, let's see. I'm going to do two things at once here. So the first thing I'm going to do, just to save us some boardroom, is that xh and xh, those are the same thing, right? I can combine them. Just like if you had x plus x, you would say 2x. So xh plus xh, I get 2xh here. So that's what this portion becomes. And now I'm going to multiply that 2 out. 2 times x squared, I get 2x squared. 2 times, I said that these became 2xh, so 2 times 2, yeah, we get 4xh. 2 times h squared, yeah, we get 2h squared. And we can't forget that minus 1 that was hanging on at the end. So I have what f of x plus h is, what that highlighted portion is. It's equal to this here. So the good news about this is that we've done the hardest part of this problem already. This is typically where I see most of the mistakes occur. All right, so before I go any further, any questions about how I got f of x plus h? I had f of x to get f of x plus h. I replaced the x with an x plus h. All right, so I'm gonna keep this portion. Let me go ahead and erase this top half. So if I want to find the derivative of the function, let's go back to this color. If I want f prime of x, I know I'm taking the limit as h goes to 0 of f of x plus h. That's what we just found earlier down here. So what I have highlighted, that is 2x squared plus 4xh plus 2h squared minus 1. That's my f of x plus h that we've been working with. All right, so I still have some other parts of my definition. I have minus f of x. What is f of x? Yeah, we have that from the beginning already. We say right here, f of x is 2x squared minus 1. And I'm just being extra careful and putting these parentheses inside to make sure I'm not accidentally forgetting a negative or a positive. All over h. All right, so if I did this correctly, there should be a ton of cancellation that's going to happen here. somehow that gets rid of some stuff on the top and also gets rid of this h on the bottom. So let's see, what do we got going on here? So on the top, is there anything that I'm noticing will probably cancel out just from the top portion of my fraction? Yeah, so first off, I got 2x squared minus 2x squared. Those are for sure going to cancel each other out. And then I have -1 minus -1. I know whenever I do minus -1, it becomes a +1. So really, -1 plus 1, I also get that they cancel each other out. So these are gone. So I'm left with 4xh plus 2h squared all over h. So this should start looking a little bit familiar to what we did last time. So I claim that there's one more thing that can really cancel out here. Yeah, I can take an h out from every single term. So really, I can say that this is the limit as h goes to 0 of, let's see, 4x plus 2h. Again, if we want to use that notation from before, or not notation, I could factor in h out from the top, and that would leave me with h times 4x plus 2h. I'm using the fact that this h and this h can cancel each other out, leaving me with this right here. So this is all according to plan. The plan was that somehow that h on the bottom would go away. So now I can finally evaluate the limit. Yeah, so now before I couldn't plug in 0 because I would get 0 on the bottom. So now that I got rid of that 0 that was going to happen on the bottom, I can plug in 0 for h. I'm going to say that again. We're plugging in 0 for h. So if I plug in 0 for h, that means I get 4x plus 2 times 0. So I'm running out of room here, but I'll try to fit it in. We get 4x plus 2 times 0, which just cleans up to be 4x. The reason that I repeated that phrase again is that I have a lot of students who plug in 0 for x. Make sure it's saying as h goes to 0. So we plug in 0 for h. Your final answer, in this case, our final answer is 4x. So your final answer for a problem like this should never have any h's in there because we plugged in for h. So make sure your final answer has no h's after everything is all done. So it seems a little bit anticlimactic. Like before, whenever we worked on this yesterday, we did all this algebra and we found out the answer was 0. In this case, we did all this work and found out that our derivative is 4x. Before I talk further about this example 1, any questions about the algebra that we applied here? Making sure, again, we're making sure that we're being really careful about our algebra. It's really easy to forget a negative somewhere along the way. This is also why algebra is one of the prereqs for calculus. So let me erase this top portion. So we're done with the problem, but there's just a couple more explanation stuff, side notes I want to make about it. So again, we did all this work and found out that the derivative is 4x. So now that I have the derivative as a function, I'm allowed to do, for example, if I want f prime of 4, f prime of 7, f prime of -2. I could figure all of those out really quickly. Instead of before where I had to do the limit definition each time for each number, by doing it this way, I have a function, and now I can just plug in each of those numbers into my derivative function. For example, what would be f prime of 4? We would get 16. F prime of 7, we just have 7 times 4, we get 28, and -8, for example. So this is almost a little bit streamlining what we did before. Again, if I had this, I would have to do f of 4 plus h minus f of 4, all of that. Do the same thing for 7, same thing for -2, and all of that. So what this function does, I like calling it our slope function. Because if I plug a number in, it's going to give me the slope at that point. So here, I plugged in 4, and I got 16. That means if I look at 4, my slope is 16. Whatever this graph looks like, again, I can show you what this graph looks like. It looks a little bit like this. Whenever I look at 4, that's going to be somewhere around here. The slope is going to be really steep going upwards. Whenever I look at -2, what's happening for the slope at -2? Yeah, it's going down. It's negative. It's a negative slope, meaning that we're going downwards, probably pretty fast if we have a slope of -8. Again, this is just rise over run. If I think about it in the classic way, that means I'm dropping 8 times every time I take a step forward. All right, so this is our limit definition of the derivative for this particular function. All right, so let's go ahead and let's see, do I want to mention this right now or not? I'll mention it right now. So what we're going to end up doing on Monday, we're not done for today, but what we're going to be doing on Monday is that we're going to find out that all of this, we have a way to streamline it and just go eventually, probably by the end of next week, you'll be able to look at this function and say, all right, the derivative is 4x without any calculation work. Technically a little bit of calculation, but nothing as intense as what I'm doing here. All right, so let's go ahead and move from here. Do I want to do this example 2 with a square root? Yeah, we can go ahead and do this one. The reason I wanted to introduce this one is that the idea overall is still going to be the same, but really it's going to be testing your algebra skills again. Let's say I have f of x is equal to the square root of 3x plus 4. Same instructions, give me the derivative of this function using the limit definition. And we know the limit definition, of course, is f prime of x, is the limit as h goes to 0 of f of x plus h minus f of x all over h. Even though I've said it before and you're probably sick and tired of me saying this, the actual calculus work we've done is very little. The calculus was, what is the limit? The algebra has been the big chunk of all of these problems. So looking at this, we're going to try to solve it in the same way. And we're going to see, do we run into any issues trying to solve it in a similar manner? In particular, square roots and radicals, there's a little bit of a unique trick we're going to have to use to try to clean up the limit. So just like before, let's focus on f of x plus h, this portion here. F of x plus h. We know that, again, this is just me looking at my original function and replacing x with x plus h. So here are my x's. I'm just replacing what I circled with an x plus h. One thing I want y'all to always be careful about for f of x plus h, this is something I always see every semester. Someone would write this here. That's going to be a different expression. That's not replacing your x with an x plus h. All you've done here is you added h. So this is not what we want here. So the good news about this is that there's not really much for us to simplify. The most I could really do is multiply out this 3. Giving me square root of 3x plus 3h plus 4. And there's not much else we can really do there. We need to be a little bit careful there because we can't really take out the 4 because you're thinking if it was 4 times, well, you're thinking more about if it was like this. Multiplication we can take out of the square root, but we can't really take addition or subtraction out. So this is f of x plus h. Doesn't seem too bad. All right, so now that I have f of x plus h, I can go ahead and use that in my original formula all the way up here. So let me erase this. We want f of x plus h. I can erase this, I'll remember that. So if I want f prime of x, I want the limit as h goes to 0 of what we just found, f of x plus h. Again, that was 3x plus 3h plus 4 minus f of x, but we got f of x. It's already here. Yeah, square root of 3x plus 4 all over a deceptively simple h. So the first thing y'all are probably noticing is what I'm noticing here is that I don't have this exact cancellation anymore because they're inside a square root. Before they were just roaming free, I was allowed to combine them if I wanted to. But here I can't combine my square roots. I can't just say 3x minus 3x, they're both under square roots. Because you can imagine that there's almost like a set of parentheses around these terms at the square root of the whole thing. So whenever it involves a square root, we have to be a little bit creative with how we really take this on. So I'm going to go ahead and simplify this. And I think I may have mentioned it for this class. I can't remember if I mentioned it for this class or the pre-cal class. I'm going to multiply by something called the conjugate. Is that a term I used in this class before? Yeah. So if y'all remember, the conjugate was saying, I'm going to look at this top expression that involves square roots. I'm going to write it out first. I'm going to multiply by the conjugate, which it looks like the exact same thing. Let's see, 3x plus 4. But I changed this sign in between my square roots. So this was a minus. I'm going to put plus here. And I'm going to do the same thing on the bottom. I'll emphasize once again, this is still perfectly legal for us because this whole thing is technically times 1. It's an ugly thing equivalent to 1, but it's still equivalent to 1. So let's see how this big thing cleans up. I'm going to take a pause here for y'all to copy that down. What was so special about multiplying by the conjugate that made it so nice? Yeah, so normally I would have to FOIL this first off because it's a binomial times a binomial. We would have a lot of square roots flying around. But the whole thing about multiplying by conjugates is that whenever I do that FOIL, FO, IL. The O and the I, the outside and inside products, actually end up canceling each other out, leaving me with the first times the first, this square root times that square root. Well, they're the exact same square roots, so I get 3x plus 3h plus 4. First times first. The other part is last times last. So I have minus, what's this square root times this square root? Well, first off, they're the exact same square root. Yeah, so I'm just multiplying what I have. Let's see. So I'm multiplying straight across here on top. And the trick I'm using is that anytime you multiply by a conjugate, it always turns out that you have first times first and then last times last. Because if you FOIL, outside you'd have these two square roots, positive. Inside you'd have the same square roots, but negative. In other words, the outside and insides would cancel each other out when you FOIL. So here I was just asking what's the last, this part times this. Since they're both the same square root, they end up getting rid of a square root. Kind of like if you said square root of 2 times square root of 2, that's going to give you 2. So in this case, I'm giving 3x plus 4 for the entire top portion. Yes, that h times this terrible looking thing. But I promise this will all clean up if we did this correctly. Anytime we do algebra, there's always if we didn't forget anything. Just because of how easy it is to accidentally forget a plus or a minus somewhere. Let's see if I can fit it here. All right, so by doing this, what do I see on the top happening? Yeah, on the top, yeah. So on the top, 3x and 3x, they cancel. Because I have 3x minus 3x. 4 minus 4. I think we agreed those cancel each other out, leaving me with 3h. So in other words, by doing this algebra trick, I changed those ugly square roots on top to be a 3h. On the bottom, I'm going to leave it alone for now because I have h times, once again, that terrible looking square root. Was it my plus 3x plus 4? I'm running out of room here. But this is still great for me. Something else cancels. Yeah, I got h on the top and h on the bottom. I'm going to take a pause here because there's a lot of things we just wrote down. So again, remember my whole deal of doing all this stuff was trying to get rid of that h on the bottom. Because I knew the h on the bottom was giving me all the problems, giving me 0 on the bottom. So let me erase this top left portion for us. So really, we haven't really done any of the calculus work. We've just done a heavy set of algebra. To recap where we're at so far, we have the limit as h goes to 0 of 3 over our super ugly square root. Plus 3x plus 4. All right, so I got rid of that h on the bottom that was causing all of the issues initially. So by following that same process as before, I should be able to try to plug in h equal to 0. So if I plug in h equal to 0, So not much of this is gonna look like it changed. Plugging in h is equal to 0. Well, there's only one h right here. Obviously, if I do 0 times 3, I get 0. So it's really what I get is 3 over the square root of 3x plus 4 plus the square root of 3x plus 4. So again, if I plug in 0 for h, that becomes 3 times 0, which is plus 0. I'm still left with 3x plus 4 here. And I can finally write my last line at long last. Can I do anything to clean up that bottom portion at all? No. Yeah, so obviously the top, there's nothing we can do there. That's a plain 3. But on the bottom, these are both the same square roots. If I gave you x plus x, you would say it's 2x. Well, if I have the same square root plus the same square root, it's going to be 2 square roots of 3x plus 4. We have our big old complicated derivative using a lot of algebra mental power. So this here is not, we're not squaring it, we're multiplying it by 2. So again, we gotta be careful about, are we multiplying by 2? Are we squaring it? Here, we're just combining 2 square roots together, not squaring it. I always dislike using 2s in my example because 2 is the weird number where it's like 2 times 2 is 4, 2 plus 2 is 4. So people get mixed up with those. Yeah, and all the squares and everything like that. But we just found a derivative. And just like before, we've done all of this algebra work. Our goal of, I believe, next week or the week after, whenever it comes around, we're going to learn about methods on how do I go straight from here to here in about 3 steps. So actually, a big part of calculus is going to be how do I find a derivative without using that limit definition that I just used here. That's actually what, bless you, that's going to be what most of unit 2 is going to be about, where I'm just going to give you a function. I'll be saying, give me the derivative. All right, so that's example 2. And I believe that that should be a good spot to stop for today. We've covered the toughest part of this section. The rest is actually just a quick thing about how do I know if I'm differentiable from a picture. All right, so I will see y'all on Monday. I did post a second homework that will be due not this Sunday, but it should be the following Sunday. Yeah, I can go over it and eat stuff. Since we're towards the end of class, if you need to go, you're obviously more than welcome to go. Let me go ahead and pull up some homework stuff.